Tomás, Alejandro. Thank you, Sandra. So, very briefly, let me thank all the participants. This is a topic that, as a matter of fact, was requested by several people in the community. So we are very happy to be able to cover this topic. As Sandra said, IPv6 only in data center network. Will go through the structure and that the IPv6 topics, and he's going to speak of the autonomous systems, and we are going to speak of the data centers. Let me give you very briefly who Tomás is. He's an electronic engineer of UBA with a FEU, and during INFAD today it's Lumen, Ericsson, Claro, and senior architect currently he's a senior architect in Vulture. Please correct my pronunciation, Thomas. And he's a founding member of LACNOG, and he's a friend of organizations. He's always been there with LACNIC. He's been a chair. And well, let's put an end to this because we could spend hours. Thank you, Sandra and Alejandro. Let me start with the presentation. I hope now you can see this screen that says IPv6 only in data center networks. So welcome to this webinar. I'm Tomás Lynch, and I work as Senior Network Architect in Vulture. Why should we have a webinar on IPv6 only in data center networks? My experience and several market studies indicate that we are barely seeing the beginning of the AI revolution, although today it may seem very marvelous. So this revolution is not just depend on the things that we can do, but behind that revolution we have the data centers that physically connect the GPU clusters devoted to processing and training large language models, the LLM. That is the basis of AI. In the data centers, we are seeing geometric growth in the number of elements in the network, and broadband, and the bandwidth, and without mentioning the number of the power that we need for these. So when the elements in the network grow, so do the number of IP addresses that we need. And we're going to see in this webinar how IPv6 is the safeguard protocol for all the addressing of huge numbers of switches and servers. So let's start by discussing the needs of a data center network that's different from an ISP, an internet service provider. The first difference between an ISP and a data center is how traffic is exchanged. While in an ISP, the traffic of customers is exchanged with elements in the internet, that is, off the network. The data center is essentially between the elements that compose the data center. I forgot to put the counter there. So the first case of the ISP, we speak of north-south traffic, and in the case of the data centers, we speak of east-west. So the physical and logical topology of a data center will be specifically aimed to providing enough bandwidth between the elements that compose its network, and as a secondary goal, but still important, is to provide connectivity to internet connectivity to clients. An example of east-west traffic is the clusters of the GPU that we mentioned before. These clusters are characterized by using a lot of traffic between nodes for their computation, for their switching calculations, that is east to west. And in comparison, there's little traffic toward the internet to give the cluster results. So If you ask a question in ChatGPT, in cloud, behind that there's a whole model that is running, and it uses up a lot of bandwidth, and the response itself is very little traffic. The ideal topology of an ISP also has three hierarchic layers: core, distribution, and access. Each of these layers have a specific role, and the size of the network element, be it a router or a switch, will depend on the number of traffic, number of clients, geographic distribution of each region, which may be a city, a neighborhood, or even a building, that each layer needs each layer. So in the diagram, we see the distribution of each element in those layers. The core forms a redundant ring. The distribution equipments collect the different access points, and the routers connect the clients. But no ISPs are ideal, depending on the geographic conditions, the density of the population, among other elements. In each region where an ISP network services are provided, you may have exceptions to the classical hierarchical topology, since its key function is to provide internet connectivity to its clients, and the traffic between clients is usually minimum. That is also why the hops between the switches of access is variable in this type of networks, as we see here. In a data center network, as we'll see later on, it is very important for these hops between the nodes, between the servers, the GPUs, always should be the same number. And also, most of the ISPs have a long history, usually going back to the commercial internet, where IPv4 used to be the dominant version, and hence the addresses delivered to the end customers belong to IPv4. And but then IPv4 was not enough to provide mass merged services of the internet, and that is why the ISP started using NAT to provide private IPv4 addresses to clients, with an end relation of private addresses to a public address. So what helped more for the extension of NAT is that the end customers of ISPs do not provide services. They only need to have access to the internet services that is usually outside the ISP network. So you may wonder why we were assigned IPv6 addresses from the beginning. The fastest response is that the client's CPE, usually the modems that were very simple, do not support IPv6. And Alejandro can speak a lot of this, but let us consider for the time being that the ISPs do NAT, since the IPv4 addresses are scarce and the clients do not provide services as websites, DNSs, or mail administrators, and an artificial intelligence structure won't be in the client's home. So the key characteristics of a data center network versus those of an ISP are the following. First of all, centralization of processing. Data centers should be able to give resources with great capacities, with the GPU power, etc. And it needs to be redundant, while between an active and a passive element it should be immediate. That is, the switches need to be all the same. Just in case one falls, then you can crashes, you can replace it for another. The second is that the east to west bandwidth is greater than north-south. So because usually the clients of that data center need a broader band for the exchanging the information between the services, and a data center network should have the fewer hops as possible, be there routers or switches between the elements. I think that this is the most important characteristic of a network that we'll see in greater detail. The next is the reduced geography. The bandwidth east to west, the processing in parallel of different units that use huge amounts of memory and processing have a great enemy: latency. It does not suffice not to saturate the bandwidth between the elements in the network. These elements should be reachable in less than 1 or 2 milliseconds without a reduced geography of just a few meters. This latency is impossible to be obtained. The fourth characteristic, the main characteristic, is the use of public IP addresses. That is the core topic of this webinar.
Olvidémonos por un momento de IPv6 y estudiemos la arquitectura física para las tres primeras características de una red de datacenter. Veremos aquí un resumen de una de las
now let us look at a summary of the main architectures that meets the features that we mentioned before, the leaf-spine architecture. If you wish to expand on this type of topology as well as on other topics of the webinar, I invite you to take part in the course on IPv6 in data centers. And this is the track of the data centers regarding certifications. So the basis of this leaf and spine and leaf architecture is the close network, and this began to be implemented in 1952. Regarding Erwin's invention, now why? To explain, this is nothing new. So Engineer Claus was seeking to find a way of reducing the necessary cross points in the so-called bar commuter or call commuter. In other words, trying to avoid being a gigantic commuter, which is impossible following the formula n times n minus 1 over 2, the result of which would be the amount of total links to communicate directly n nodes amongst themselves. So this implementation was called a commuting network in multi-stage circuits. Each client of a closed network has to go through different commuters or stages in order to carry out a call between 2 points. These stages are called entry, mid, and exit. So this is what we call a 3-stage commuting network. So if you want to have some more history, I recommend checking the links that we have included, and this shows that not only is it in data centers and in telephone switches have the closed networks been used. These have also been used. The concept of closed network has also been applied to designing VLSI circuits and to produce the modern routers, and more recently in machine learning. So a spine and leaf network is simply a closed network in 3 stages: entry, median, and exit. So leaf, spine, leaf. So the customers of this network, please let him know that the slides do not appear on the screen. So the servers connect to the leaves of this network, and each leaf, absolutely every single leaf, gets connected to all the spines in that network. So he says he got lost. So there are no physical links between the leaves and the spines because I need the same amount of hops between the servers. Server leaf 1, server leaf 3, and so on. Now, these connections are not necessary because the interruption of a spine does not affect the communication of the servers between themselves if the remaining links support the bandwidth east-west. In other words, if a spine crashes, the network does not become saturated. So the first advantage of a leaf-spine network is to be able to grow horizontally in a rapid and straightforward way without affecting the network that is in production. So adding new clients is as simple as adding a new leaf and connecting it to the spines. Now the second advantage is related to the increase of bandwidth between the leaves. Adding a new spine or also adding a second link between the leaves and the spine. will allow us to increase the bandwidth once again without affecting the traffic that is in production. So this is a network that is in production, and adding new elements or leaves or links will not affect the traffic that is taking place at the moment. Now, so the disadvantage that we can mention is that the amount of links is significantly higher compared to the full mesh, and that they can lose a lot installing the physical infrastructure. So let us assume that the leaves in that graph are connected with 3 interfaces of 10 gigas each one per spine. So this will be a total amount of 12 fiber links, and the bandwidth supported by each leaf is 30 gigas. Now let us make a full mesh of the leaves. Each leaf has 3 ports of 10 gigas each, and this leads us to having 18 links compared to the 12 of the architecture that was presented. Many will say that the cost of 18 direct links is less than the 12 of the spine and leaf topology. So I'm also investing money in 3 switches. Let us imagine that we add 4 further leaves to the presented topology with the same bandwidth per leaf of 30 gigas. So with the topology on the screen, we can only connect 12 new links, 3 for each link, with a total of 24 links. In the full mesh, things become more complicated because the amount of links that have to be added is 66, if my maths are not wrong. Now, this is because the full mesh function is quadratic and the spine and leaf function is linear. In this section now, we're going to see routing options in this type of topology, and I will also tear down a myth, by the way. Now, the first combination of the routing protocols that a traditional ISP engineer would think of would be BGP plus OSPF. We have the core routers, the distribution routers, and this would be our 0 area, and the access routers will be positioned in different areas. Don't forget the not so stubby areas, please. And then for IBGP, because we have a lot of routers, we're going to put 2 good route reflectors connected to the 0 area of the central house. Now, in a very symmetrical network such as that of a spine and leaf, where all the links are equal, the switches are also equal. So nothing could be better than a good OSPF where I don't have to configure any metrics. So definitely this will work in a spine and leaf network and sounds like a good idea based on a ghost that follows us engineers of the BGP network, which is difficult. So we all are aware of the the greater route local pref, which is a preferred one. So what would happen if the network would be IGP, EGP? How can I compare how old it is? But I can ask the following questions. Why is it easier to do the not so stubby area with the entry BGP and exit BGP routers have? If the BGP is so difficult, why do we configure IBGP so naturally? And if we look at the words quoted by Ivan Pepelniak in the quoted link, BGP is a simple protocol that can be adapted and we can use for the specific adjustments that we have to use in our import and export policies regarding prefixes that are so common with the transit providers. So in a symmetric network where all the links have the same speed, where all the routers in the same layer comply with the same function, BGP as a single protocol is an excellent option. And this is the option that I will share with you now. If we use BGP as a single routing protocol, then we have to use external BGP or eBGP. This avoids having to use the malicious next hop self so that IBGP without IGP can work correctly. And in case you don't believe Ivan or me of Alejandro, please read chapter 5.1 of RFC 7938, where, among other advantages, we have the following. First, the ease of doing follow-up of the problems. If we use an assignment cone for the autonomous systems, an AS path is simpler to follow than several next hops. For example, a route with AS path 65,001 will indicate that the prefix generated by leaf 1 is generated by leaf 1 and is in that path precisely, whereas a prefix with the AS path 65,002 indicates leaf 2. Secondly, the export and import policies of eBGP will be very simple and will largely depend on the information that we generate in each layer. These policies can send and receive all the prefixes, or the leaves can send all the prefixes but can only accept one default route. So we'll have very many options of policies between the internal BGPs peers if we think about this properly. Now, BGP also has some features shared with the IGPs to add prefixes, to remove the private autonomous systems, which is part of concealing the internal structure, to external peers. Equal cost multipath, or ECMP, can allow to do traffic balancing between peers with the same or with a different autonomous system. So in this way, traffic is balanced between spines and leaves. So my recommendation is to use one single routing protocol to external BGP.
Volvamos entonces a IPv6, que para eso vinieron. Se estarán preguntando.
So let us now go back to IPv6 for data centers.
Redes de data centers, solamente IPv6.
The advantages for IPv6 only data center networks compared to dual stack is one of the discussions that we also have when we speak about IPv6. Books and philosophies have been written about this. And people laugh when I say dual stack doesn't solve anything at all.
Dual stack is simple.
No, dual stack is simple. Each device, each interface has two addresses, an IPv4 and an IPv6 address. In other words, it doesn't solve anything at all, the issue of the lack of IPv4 addresses, because we are using these precisely. So this leads to different sorts of headaches. Commercially, if we don't have IPv4 addresses, then we can wait from 2 to 5 years until prefixes are released from the RIRs. So we can buy or lease IPv4 addresses, but no matter how much money we have, we always run the risk of receiving addresses that are not totally clean. You might think that these might be assigned to a spammer, might have been assigned to a spammer, and the reputation of the prefix will be quite poor. Now, technically speaking, it's about duplicating all the configurations to assign two IP addresses to each of the devices, each of the interfaces, to configure two different BGP sessions with the same router, and then, in the future, to plan how to remove obsolete addressing. Now let us think about major data centers. I always think that no matter how small our company is, we always have to think and plan thinking big, to think about future growth. Today, a GPU network might easily have more than 4,000 nodes. All this without considering the spine and leaf infrastructure that is used for these types of networks. IPv6 is what today allows us to set up networks of this size. So if the excuse for configuring IPv4 still is that not all networks have configured IPv6, let us recall that the transition protocols are being used more and more, leading to an ongoing maturity of them, and these are becoming more and more IPv6 and efficient. Now let us have a look at the tools we use to deploy a data center only using IPv6. Let us start with the assignment of IPv6 addresses, how we're going to divide a prefix assigned by LACNIC in larger prefixes. In other words, subnetting. Now, the practice has been outlined by RIVE 690, and you can access this in this QR code. This was written in October 1997 by Jan Schorsch, a friend of ours, and shows how to assign prefixes to our clients. So this explains how we assign different prefixes. This has been considered. For example, we can see recommendations for prefix delegations to a home CPE. This is also useful for assigning prefixes in a data center.
In a nutshell, this BCP indicates that we could assign /48 to our end users, that is our clients, and if we wanted to be a bit more conservative, we could assign /56. But it is not advisable to give assign more than /56, that is, for instance, /72. The only problem that /56 have is that they're not routable internet, just as an internet provider does not accept prefixes over of IPv4 over /24. In IPv6, they don't accept more than /48, and in this case, we use /48 blocks as a basis to assign to the components of the network that require IP addressing. And here we have we need to change the way we conceive IPv6. And personally, I think that the most difficult part of IPv6 is to quit thinking as we did in IPv4. So you have to dive into the IPv6 mentality and forget what you learned for IPv4. One of the most typical examples is the addressing of IPv addresses to the host of computers that need only one IP address. From the point of view of IPv4, each host has a single IPv4 address. For instance, 192.0.200 of 192.0.2.0/24 could be seen as 192.0.200 with CIDR/32 as if it were a cult. With thinking like this, when we enter the IPv6 world, and it's very likely that we'll feel tempted to assign a large prefix to a computer connected to a network. This prefix may be a /127, or thinking of /24 and assigning, and here Alejandro will laugh, a /104 to the LAN network where the machines get connected. All this is based on the fact that we need to be careful not to spend IPv6 addresses just in case we run out of them, as it happened with IPv4. But the case is not like this with IPv6. So let's start with our arithmetics. First, let's see the simple things. An RIR like LACNIC typically assigns a /32 that has 4 trillion /64s. Each /64 has 1.8 times 10 to the 19th addresses. That is a 1 that is /128 in 1/32. That is that the total number of 128 in /32s are many because, but many addresses, as many as 7.2 to the 10th to the 28th. And if you're not surprised, I just propose thinking of the Ed Holy as I did it in high school. So we summarizing Ed Horley's calculations, if we assign a /64 to a host, and if in every second you use 10 million addresses, it would take a host 58,000 years to use all those addresses. Just calculate it and go and see that, and you'll see that I'm right. And finally, it would be ideal if the IPv6 addresses would configure on their own. As proposed in our FC 2373, we could use a /64 assigned to a host, and that it may auto-configure the 64 bits of the host used in the MAC address in the machine. So people used to debate what prefix to assign to a link between two routers. We already saw what prefix to assign to the interfaces. There was even an RFC saying that you shouldn't use /127 for these connections. This RFC 3627 today is obsolete, and the IETF recommendation gives a number of reasons in RFC 6164 to use the /127s. The truth is that finally there are two prefixes that may be assigned, and there's a reason for each of them. On the one hand, RIPE 690 and RFC 2373 propose using /64s to leverage on the self-configuration and addressing of EUI 64. None of them opposed to using /127, but the only thing that RIPE 690 say is that those /127 should always be the same /64. On the other hand, RFC 6164 provides enough security reasons for using /127s between the links of the two machines. Finally, if you know that a port that supports IPv6 may have a local address, we could work with no public IPv6 blocks and base all our network in these link local addresses, as we'll see later on. Remember this, the link local addresses, because this is the most important thing in this webinar. So, thinking as we did with our IPv6 mentality, let us see the number of elements that are handled in a data center network for GPU clusters. That is, dimensions in the era of the artificial intelligence, and you'll get scared with numbers. In the networks for AI, there are many servers. Clusters from 1,000 to 32,000 servers are the rule in this world, and these servers are connected to two leaf-spine networks with different goals. The first network is the back end, and there you exchange information for training the cluster, and all the GPUs should be capable of communicating with the rest of the GPUs using all the bandwidth possible of the interface. This is the definition of a non-blocking network. That is, that it doesn't have over-subscription. This backend network consumes all the bandwidth available and should be fast enough so that the model training will be more effective. The second spinal leaf network is the front end. This network is in charge of receiving the queries in the cluster and delivering the results. And here, yes, you can have oversubscription of the links depending on the number of queries that you have per second. Now let's see the numbers. So let's give an example of a cluster with 1,024 servers or 8,192 GPUs, since usually each server has 8 GPUs. Again, this is a small to medium-sized cluster. So to see the number of spines and leaf switches that we need in each network, we need to consider that each server has two links to the front end for redundancy, and each GPU has one link to the back end. Then we know that the back end network does not have oversubscription, and for the front end network, we take an oversubscription of 1 to 4. We put all the numbers in a blender. I won't bore you with the mathematics here. You can write to me if you wish after this webinar. And the results are as follows. For the backend network, we'll need 192 switches. Of 128 ports, 100 gigas. All of the links have 100 gigas. The links between the backend switches are 8,192 links. That is the number of GPUs. For the front-end network, this is more modest. We only need 24 switches and 1,280 links between the leaves and the spine in this network. The numbers for this AI cluster, these are alarming numbers. So let's leave aside who will cable all the switches and who will pay in money for all those switches and all the wiring, and let's give the number of IP addresses that are necessary, and the numbers are also alarming. If we were to use IPv4, for instance, for the public addresses, they would be a /21. In IPv6, this would be covered by a /48. Let's remember that the RIRs as SLACNIC usually provide their members a /32, and these /32s are 65,000 /48. We see the first advantage of using IPv6. However, even if we use IPv6 addresses, it's very hard to maintain an IP address administrator or IPAM. For the hosts, we don't have any other solutions than assigning a /64 and confiding in Slack. For the switch loopbacks, we can assign /64, so /128, but we must assign them in a certain manner. They must be public addresses. If we are for the servers, they have to be public, and for the switches, we can use private addresses of IPv6. And all these addresses need to be registered somewhere, so as not to reassign an IP address that is already being used in one machine in another. For the 94,000, well, notice that, let's take this. So we said, for the servers, we need 2,048 public addresses, 16,384 private addresses. For the switches, we only need 216 loopback addresses and 9,472 prefixes for links. If we see the numbers in IPv4, we see /21, /18, private. These may be private addresses, but there are a lot of addresses. And in the IPv6 too, the /48, although it's easier because we have 3 /48s and 1 /64, there are many addresses. So for the 9,400 for the links between leaves and spines, we can use IPv6, and while we may forget the address that we are assigning the links, it is not even necessary to register them in, and let's see how. So how is the link local addresses? So if we to forget what are the links, the addresses that we assign, we can use unique single local link local. described in RFC 4291, and here we assign FE80 :/10 unicast addresses. In practice, it's only FE80 /64, and this is you configured in all the interfaces that support IPv6, regardless of whether they have an IPv6 address. This prefix is used for the automatic assigning of global addresses such as Slack, and for the neighbor discovery protocol in NDP. That is, these addresses, this link local, if we turn on a machine, a router, and you say, I want to have IPv6, you have the public IPv6, and at the bottom, an address that starts with FE80 something /64.
So if BGP needs an IP address to maintain a peering session, why not use these link local addresses to these sessions? In other words, let us use the link local addresses so we can forget to assign IPv6 addresses, because these are IP addresses ultimately. This is for peering, we can use the link local addresses. So this example shows the network elements that have an IP address assigned to it from two different /48s. The switches of the block 2001 DB8 64/48 and the hosts of 2001 DB8 AA/48. The links between the spines and the leaves will not have configured any global unicast IPv6 address. That is why this diagram shows FE80 :/64 in italics, because we needn't worry about the addresses, because these will be assigned automatically. Now let us pause here to analyze the autonomous systems number. Each leaf has the different autonomous systems, and the spines share the same autonomous system, which is different to that of the leaves. This is a good practice, because when sharing the same AES, the prefixes are spine 1 are not propagated to spine 2, and vice versa. So I was saying, this assignment is a good practice, because when sharing the same AES, as I was saying, the spine 1 prefixes are not propagated to spine 2, and vice versa. The leaves, because they have a different AS, accept all the prefixes of all the other leaves. Here I used these autonomous systems. These are private autonomous systems of 32 bits each and more bytes, but you can use these with the traditional autonomous systems of 65,500, for example. So let us go and see what we all like. Configuration. This is a configuration of a leaf using link local addresses and global unicast. Configuration is for a switch with FRI. I don't like to use brands in these webinars, but nevertheless. First we have the configuration of Ethernet 1 to spine 1 and Ethernet 2 towards spine 2. Ethernet 2 and Ethernet 1. Ethernet 3 connects the host of the data center. And finally, we have a loopback address. We can clearly see that Ethernet 1 and Ethernet 2 don't have any IPv6 addresses explicitly configured. Now you will note that the neighbors are not IP addresses. So these neighbors over here are no IPv6 address, sorry, IP addresses. And neighbor Ethernet 1, neighbor Ethernet 2 interface. And these options have the name of the interfaces, as we said, and the option interface is added. Here we have 2 sessions enabled in the unicast IPv6 families. Down here we see how this is enabled in the IPv6 unicast family. Now, within this family, we're also propagating the loopback addresses and the server address. So the loopback prefix, in fact, and the prefix of the server. The other leaves, in leaf 1 we had 4, they have similar configurations. The BGP configuration of the spine is similar to that of the leaf. Each interface of the spine is a BGP neighbor with a different autonomous system and only enabled in the unicast IPv6 family. And once again, we have enabled this IPv6 family enabled. Now, the only IP address that we need to propagate is that of the loopback of the device. The configuration of the switches then, well, here we see something that is quite straightforward, and you can do this using link local IPv6. So the configuration of the switches is easy to automate and can be programmed because the leaf spine network is always the same. We'll always have 3 different stages: leaf, spine, leaf. The rules to configure the devices are straightforward, and we can configure and reconfigure all the devices easily. If we had a 64-port switch, we have 10 spines of 64 ports. In port 1, I'm going to connect leaf 1 to each of the spines. In interface 2, I'm going to connect leaf 2 in each of these spines. If in the future I add a further spine, I will then take the link of leaf 1 and connect this to port 1, the link of leaf 2 to connect it to port 2. In other words, the configuration is much simpler. We can have templates that are far simpler. And the configuration is very, very simple. We don't have to think about IP addresses. And here I had posted in LinkedIn a few days ago that this webinar was going beyond the fact that we are going to die because there won't be any more IPv4. I don't know what we're going to do. So let's use IPv6. And many people out there in recent months, and with good intention, I suppose, people who have been working with the internet for many years and people from LACNIC, and I would never say no, are now saying, well, IPv6 is not that good. I don't know whether I should use it or not. Now, I think that this precisely is one of those cases where IPv6 makes configuration easier. So configuring with IPv6 is much simpler. With IPv4, these neighbors would be 192.1, point I don't know what else, and so on, and slash that is on the policy. Now, in this way, it is much simpler, far more straightforward. We can have the templates, and whenever we add a device, the configuration is instantaneous. I don't have to stop and think about the IP numbers, except for loopbacks. I don't have to think about whether it's a /30 or a /48 or a /64. So I use the local addresses, and this is what helps me. This is one of the advantages of IPv6, which is essential for the data center networks. This is namely the ease of not using any address to conceal our IPv6 addresses. So we're using addresses, but I don't have the need. So that is the message of this webinar, if you didn't realize. So now what happens if I still want to use IPv4? There's a whole world out there that only works with IPv4. For example, there are many online games that still use IPv4. And I have insisted again and again that they should use IPv6 and say, well, no, we're doing fine with IPv4. So there are some apps that still use IPv4. The most famous one, I think, Spotify at some moment. I don't know whether it still is that. I don't want to say anything that is wrong. I might be mistaken, but there was an app of that kind that used only IPv4. Skype at a given moment, but that has already extinct, but it only used IPv4. So how do I connect this data center to an IPv4 network? So there are two possibilities. Henry Godoy is among the participants, and I hope he won't kill me after what I say now, but he's also an expert in IPv6 only compatibility with IPv4, and of course Alejandro. So if we want to use IPv4, there are two options. One is to number the servers with IPv4 addresses, to use dual stack in the servers, to assign to each server a public IPv4 address. However, it is not necessary to number with IPv4 all the network switches. You can configure the switches so that they propagate IPv4 prefixes using an IPv6 NECT hop, as has been described in RFC 5549. And let me remind you now that a /22 that has 1,024 addresses costs about $40,000 US. Now, the second possibility is to do NAT64 and DNS64 using methods such as SIT-DC. These methods maintain the tables and map the IPv6 and IPv4 addresses. Now, for reasons of time, I recommend watching this webinar. I won't explain this now. This was a webinar by Eduardo Cano on Joule, open source tool that used NAT64 and SIT. So conclusion, compared to an ISP addresses, a data center network can be easily configured and see how the topology will grow in the topological radius. So if you add more servers, then you will add more leaves, and if it is necessary, more spines, but always within the space assigned to the walls of the building. The networks of a data center use large amounts of devices and links, and therefore many IP addresses. So all this makes IPv6 the ideal candidate to assign IP addresses to the elements of a network. The benefits are a large number of addresses, and using IPv6 links local simplifies configuration. We can forget about a numbering scheme, the interfaces between the switch. You can forget if the BCPs is a /127 or /126 or /64. And simplifying configuration, you can program this to be able to deliver things more rapidly and free of errors. You can configure a network that is ready to be placed in production. So using IPv6 in a network of services of a data center not only is guided by the scarcity and cost of IPv4 addresses, but also is driven by a larger efficiency and the configuration of this network. So 1 hour is a limited number of time. I didn't go into the details. Now let me highlight a couple of things. Let me remind you that there is a course in the campus. For those who haven't heard about this, Tomas will be giving a course in the campus. It's a great course. I recommend those who are interested in the topic to do this. You also referred to Joule. There have been webinars on Joule in all the LACNIC courses and events. We have referred to Joule. So there are many videos and LACNIC, and we have covered these topics on many different occasions. Now we have time for 3 questions only. So the first question is from Edmundo Casares. He was asking, the interconnection of the servers and the GPUs is a hypercube. Wow, what a question, Edmundo. Well, he's a friend of ours. You killed me there, that question. I really don't know what the definition of a hypercube is. I know it has a lot of connections, and I'm also aware that the GPUs and the GPU servers internally, if the GPU of a server wishes to communicate with the GPU, if the GPU 8 of a server wishes to communicate with GPU 1 of another server, it has to go through that switch. But I don't know whether that is what you're asking. I owe you that answer. I did some AI to understand the question. Thank you, Alejandra. So Henry Godoy congratulates Thomas for the presentation and showing the importance of IPv6 for the growth of the internet. And thank you, Alejandra and Sandra, for choosing such an important topic. This topic was chosen by the community. So if you wish us to find a speaker on a given topic, please let us know, and we really will be glad to do so. So now, because we have no more question, I'm going to ask a question myself. But don't ask me a question like Edmundo's, please. No, it will be somewhat more complicated. Alejandro, sorry to interrupt. There's a question in the chat.
Yo la tengo aquí. Dice, para el esquema Spine and Leaf en la
For
marca
the Spine and Leaf scheme in the Cisco brand, what models would be the ones for Spine and what models would be for Leaf? Well, I'm not aware of the Cisco brands. I know Juniper, which are the QFX5240, and these can be used for Spine and for Leaf. I know Cisco had the Nexus, but to tell the truth, I wouldn't know what brand these would be. There are also a lot of white boxes like Cumulus and switches and Dell switches that use FRR and BIOS, which are all open source. There's a lot of that out there in the Leaf and Spines and white boxes. You have a switch and you put the OS you wish. That's a good point. And you know, when you showed the configurations, Thomas, I couldn't stop noting that you had the BGP command and the multipath relax. So I was asking whether it would be useful that on the left side, this is the best path. My question is whether it is normal that in the data center world, well, we explained this command, but maybe you can expand on this. Is it normal to use that? The point is that normally, as you can see over here, we have a BGP session per interface. If Leaf 1 is connected to another phase, it is connected to Ethernet 1 and Ethernet 10. I'm not going to do link aggregation. I'm going to have a session on Ethernet 1 and another on BGP. So the best path and the multipath that is relaxed is precisely for that, to use the two links to balance traffic between the two links. Now this is because if I don't have that command, this is what we call equal cost multipath. If I didn't have that command, I'm always going to select one of the links. So all the traffic will go through the other link, and the traffic through the second link would only go there if the first one crashes. So using AS path multipath, I can use the two links. Now, why relax? Because the multipath configuration, if I only use he corrects himself, BGP best path, he corrects himself. If he uses BGP best path AS path, this will only be equal cost multipath or SMP if I see the same autonomous system. And this will happen over here. Now, for example, if I have to send it from the leaf towards, send it from the leaf to the spine, I am going to have two different, no, he corrects himself, the same autonomous system. I'm trying to figure out where I would have this. Okay, and nevertheless, the idea is to do SMP, to use all the links, all the BGP sessions to forward the traffic. Great. Excellent answer, and I'm very thankful. Now, to close, Tomas, we have a question stating, could we virtualize spine and leaf? Maybe a lab, maybe you can. There are devices that allow you to virtualize this. You can use servers and have a virtual route. I don't know whether the question is aiming at that. I can put that in a common Linux. And I have a Linux server with 4 interfaces to FRR. And there is an IPv6 net. He doesn't recall the command. You have that in Linux, you put 1 and it doesn't do backward forwarding. Now, if the question is referring to whether this can be done in a virtual lab, yes, there are tools out there. I'm recently using NetLab a lot, which is from Ivan Pepelniak, whom I mentioned in this presentation. Container Lab. Well, NetLab is based in Container Lab. And then there are others. I don't use these, but you have GNSTIC 3 and others that I don't quite recall. Okay, thank you. To close, at LACNIC, we use a lot GNSTIC 3 when these are more than 3 days, and we also use Container Labs when these capacity building, the training courses are shorter ones. And this has to do with the packet capture is easier in GNSTIC 3 compared to Container Lab. Not everything, this depends on your choices, your preferences. Regarding the course authored by LACNIC, this is available in the campus and it has practice sessions. So I think there are no more questions now. Tomás, thank you very, very much for your time, for your support, for sharing your knowledge with the community. And Sandra, do you have any closing remarks? Over to you. No, I have nothing else to add. Thank you once again. Thank you, Thomas. Thank you. Thanks to all the participants for having joined us in this webinar. If you have any questions, let me remind you that you can send an email to training@lacnic.net. So see you in a future LACNIC session. Thank you once again. Thank you, everyone. Have a great day. Thank you.